Okay, so I'm going to introduce some rules of probability, and I'm going to do so while showing you some examples. So let's dive right in and take a look at what we have here. The jar contains 12 caramels, 7 mints, and 16 dark chocolates. What is the probability of selecting a mint expressed as a fraction? So we're looking for the probability of coming up as mint, and we want our answer to be a fraction. Now, in my last video, I said that our numerator would be the number of ways we could achieve our event, okay? And that our denominator would be the number of things in our sample space. Well, our sample space is the total number of candies we can pull out. There are 12 caramels plus 7 mints plus 16 dark chocolates in there. If we're reaching around blindly and grabbing the first candy we get a grip on, there are a total of 19, 25, 35 things that can happen if I've added that correctly. Hopefully I have. So this here on the bottom is our sample space. It's everything that can happen. Now our event, up on the top, our event is just the number of things in the activity that correspond to what we want to happen, what we're talking about, what we're trying to find the probability of happening. We're trying to find the probability of getting a mint. Well, according to this, there are 7 ways to get a mint. That's it. So the probability of getting a mint is 7, the number of items in our event. Our event is winding up with a mint, and that will also be our numerator. Our denominator is everything in our sample space. Our fraction is 7 out of 35. That is our probability. Another fun thing about probability, you always have to wind up. The probability is always somewhere between 0 and 1. It can be 0. 0 means what you're talking about cannot happen. 1 means what you're talking about has to happen, under reasonable circumstances at least. And your probability is always somewhere in between. So if your fraction that you get is negative, if your fraction is greater than 1, you've made a mistake somewhere. You cannot have more than a 100% chance of something happening. You cannot have more than a probability of 1. So we got a fraction in between 0 and 1. Doesn't necessarily mean can't always assume that means you're correct, but in this case, if we had gotten greater than 1 or less than 0, we'd know we were wrong. All right, let's take a look at the next example I have here. The numbers 4 through 14 are placed in a bowl and drawn at random and then replaced after being drawn. Is it likely or unlikely you will draw a number less than 7? Okay, so the numbers 4 through 14. These are hard to visualize. I'm assuming they mean numbers written on a piece of paper. So first off, what's in our sample space? Well, our sample space is 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. That's our sample space. That's everything that can happen. That is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 things that can happen. Sometimes it's good to write out the list if the list isn't too long. A lot of people see something like 4 through 14 and they assume there'll be 10 things in the list. But if you include the beginning and end, it's actually 11 total items. That's our sample space. Our event, on the other hand, that we are talking about is if we come out with a number less than 7, that is 4, 5, and 6. There's only 3 things in our event. So the probability of pulling out a number that is less than 7 is equal to the 3 ways our event can occur. You pull out a 4, 5, or a 6, divided by the 11 things total in our sample space. number of ways your event can happen, divided by number of things total that can happen. That's how you find the probability. Now there's an interesting phrase in here. Drawn at random and then replaced. Replaced becomes important because on some of these examples we are going to start talking about how what's the probability of 2 things happening in a row. It's probability of 3 things happening in a row. There are rules for that, but the rules depend on whether or not the first event changes the situation. You see, if I walked up and pulled a number out of the bowl, and I kept the number, then when the next person went to pull a number out of the bowl, there would no longer be a denominator of 11. It would change the denominator. We'll get to some examples of that. Okay. Here's another situation. In a deck of 52 playing cards, are the odds favorable that you will draw a heart or diamond? Well, your first question might be, what does favorable mean in this case? Favorable is an adjective that we all probably know what it means. Some of us may not remember how to spell it on the first try. Favorable has a very specific meaning here. It means the probability is greater than 0.5. It's more likely than not that you will have this outcome occur. So the question is, are the odds favorable that you will draw a heart or a diamond? Will we get a probability greater than 0.5? Now, every once in a while, I find one of my students actually doesn't have a lot of experience with playing cards. Sometimes they do, sometimes they don't. Sometimes a visual is helpful. If you don't have much experience with a deck of cards, this might help. So here's a deck of cards. There are 13 cards in each suit. There are 4 suits. Our sample space consists of all the cards. We have a sample space of 52 cards. I'm not going to list them all this time. Sometimes it's helpful to list everything in your sample space. Sometimes it is a waste of time. This is definitely not the best use of our time right now. 52 cards in our sample space. What's the question again? First question is it favorable? Will we get a probability greater than 0.5? Well, we need to find the probability. Are the odds favorable to draw a heart or a diamond? There are 13 cards in the heart suit, and there are 13 cards in the diamond suit, and you are just pulling 1 card. So our probability then, the probability of a heart or a diamond equals, well, let's see, there's 13 hearts and there's 13 diamonds out of 52 cards. That is 26 out of 52. That is exactly 0.5. It's exactly 1/2. Are the odds, I shouldn't say odds, that has a slightly different meaning. It's a question for, it's a different course to teach you that one. The probability, keep using the word correctly, the probability is exactly 0.5. That's not favorable. It's not unfavorable. It's not bad. It's perfectly even. So we cannot say it's favorable. Our answer has to be no. But I'd like to take a minute and mention one thing I did here. This little addition. Why did I do that? We had 2 events, okay? 2 events going on. I'll give you a rule through this example. If you are finding the probability of 2 or more events in one experiment, if you are trying to find the probability of 2 or more events in one experiment, what do I mean by that before I even finish the sentence? I mean, pulling a heart is one event. Pulling a diamond is a different event, but we're only pulling one card. We're only doing one activity. We're pulling one card out of the deck. But we're willing to count either of those events. Well, if you're trying to find the probability of 2 or more events occurring in the same experiment, you add the probabilities. Doing one experiment, but more than one event is in your probability, is what you're trying to determine. Add the probabilities. That's why I took the probability of pulling a heart and the probability of pulling a diamond, and I added them. Okay? So there's another probability rule for you. Next example. There's a jar of jelly beans with the following flavors. 12 are grape, 17 are blueberry, 5 are pineapple. 12 grape, 17 blueberry, 5 pineapple, and 13 are coconut. What is the probability expressed as a percent of selecting either a grape or blueberry, replacing it, and then a coconut or pineapple? Okay, we're going to start another rule. This one's a little more complicated, so I'm going to give you the rule first. Here's the rule. When you are trying to find the probability across multiple experiments, you multiply. This is confusing. One minute I'm saying to add, the next minute I'm saying to multiply. Seems confusing, right? Okay. This is where knowing your words can be helpful. The better you understand these words, the difference between an event, sample space, and an experiment, the easier this will be to keep track of. Let's go back a moment. This was one experiment. You were pulling a single card. You were just doing one thing. When you're doing one thing, but you want to know the probability of multiple events being a part of one of those things, multiple events can satisfy your one successful outcome to your experiment. You add those probabilities. We would be just as happy with a heart as a diamond in this case. So we add the probabilities together and we conduct our one experiment. This is not one experiment. This is the experiment of selecting a grape or a blueberry, replacing it, and then selecting a coconut or a pineapple. It's 2 different experiments. And if you want to know the probability of an outcome at the end of 2 experiments, you multiply instead. So let's see how this plays out. First, the probability of selecting either a grape or a blueberry is the probability of selecting a grape plus the probability of selecting a blueberry divided by the total number of elements in our sample space. What are the total number of elements in our sample space? Well, that's the 12 grape we could pull out one of, or the 17 blueberry, or the 5 pineapple, or the 13 coconut. Probability of a grape or blueberry is the number of ways we can pull out a grape plus the number of ways we can pull out a blueberry divided by everything in our sample space. Now, one asks for a percent, but we'll get to that in a second. That's first experiment. Every single thing you do is an experiment in probability. Our second experiment is the probability of pulling out a coconut or a pineapple. And that is well, how can that happen? There are 5 ways you can pull out a pineapple. There's 5 of them in there. There are 13 ways you can pull out a coconut. Number of things that can happen total is you could pull out a grape or 17 or a pineapple or a blueberry. So, in this experiment, we have two events, pulling out a coconut or a pineapple. In this experiment, we have two events, pulling out a grape or a blueberry. To find the probability of pulling out a grape or a blueberry, we add the number of ways the events can happen, divided by everything that can happen. To find the probability of a coconut or a pineapple, we add the number of ways either event can happen, divided by the total number of things that can happen. To find the probability of one of these things happening and then the next, we multiply these probabilities together. So the probability of both is, well, 12 plus 17, that is 29 over 37 over 47, if I've added this correctly. I'm actually going to pause here and double check for a moment. Yep, pretty happy with that one. And then you multiply that. 5 plus 13 is 18, also times 47. This first fraction, just to be clear, this fraction is the probability of getting a grape or a blueberry. Then I put that back, and this other fraction is where I find the probability of getting a coconut or a pineapple. They want the final answer expressed as a percent. Don't think it's the best use of our time to watch me multiply these numbers out and turn it into a percent. So I'm going to pull out one of my favorite visual calculators here. And I'm going to write the fraction 2947 times 18 over 47. This will give me a decimal. How do I make a decimal into a percent? I multiply times 100. I ask this, my script calculator, to calculate it, and it tells me that we have a 23.63% of pulling a grape or a blueberry, putting it back, and then pulling out a coconut or a pineapple. That is 23.63%. So again, if you want to know the probability of multiple things happening in a single experiment, you add them. If you want to know the probability of a particular outcome after multiple experiments, you multiply them. Okay, let's try another example, see if it helps solidify these rules. In a deck of 52 playing cards, what is the probability of, as a fraction, of drawing a picture card, replacing it? So we draw a picture card, ace, king, queen, jack, replacing it, and then drawing either a heart or a diamond. Okay, we can do this. Probability of a picture card. Let's bring back our visual help for the deck of cards. There it is. Okay, so if we're looking at our picture card here, our deck of cards, let's get a better color for this one. Okay, the picture cards are jack, queen, diamond, or ace. And each of these picture cards can occur 4 different ways. So I have highlighted 3 times 4, 12, plus 4 more, 16. So if I'm counting correctly, the probability of a picture card is there are 16 picture cards. That's the number of items in our event. Divided by 52, the number of cards in the deck, that is the number of elements in our sample space. That's our denominator. Probability of a heart or a diamond, we figured out before. There are 26 hearts or diamonds, adding the 13 diamonds to the 13 hearts, you get 26 total out of 52 cards. The probability of these two things happening right after the other, when you put the cards back, is 16 over 52 times 26 over 52. Now, it says to leave this as a fraction, so let's see. Pull out the calculator, turn it back into a fraction, but sometimes it might be even a little easier to reduce things a bit. If you divide 16 by 4 and 52 by 4, you get 13 over, 4 over 13. If you divide 26 by 2 and 52 by 2, you get 13 over 26. Actually, you get all the way down to 1/2. The 2 can reduce with the 4 twice. So as a fraction, this should be 2 divided by 13. 16 over 52 should simplify to 2 over 13. That is the probability of getting a picture card, putting it back, and then getting either a heart or a diamond. We're going to come back with some more examples and show you some even more interesting tricks for counting, creating fractions, and determining probability.